This photograph shows a tiered garden fountain, and we are going to use its physical structure to ground our study of abstract circular geometry. The perfectly circular basins serve as our primary geometric subject. If we extend the straight edge of the stone path so that it grazes the very edge of the circular grass patch, intersecting the boundary at exactly one point, we create what is called a tangent. The singular, precise coordinate where the straight line and the curve meet is defined as the point of tangency, or the point of contact. Now observe what happens when a path takes a more direct route. A line that completely slices through the circular basin, intersecting the curve at two distinct points, is called a secant. A secant can be an infinite line, a ray, or a segment, extending beyond the boundary. But the specific finite segment trapped entirely within the circle's interior, connecting those two intersection points, is called a chord. This distinction between touching the boundary and crossing it sets up the mathematical rules that govern the entire structure. We can scale these single lines up to form complex shapes bounded by the circle itself. In this diagram, a polygon sits inside the circle. Because every single vertex is locked onto the circle's perimeter, every side of the polygon acts as a chord. This is an inscribed polygon. When an inscribed polygon sits perfectly inside, the outer boundary itself is referred to as a circumscribed circle. We can invert this relationship. If the circle shrinks until it sits inside the shape, we have a circumscribed polygon. Here, every side of the exterior shape acts as a line segment tangent to the interior circle. These boundary relationships lead to strict geometric laws, like Theorem 6.2.1, which defines the cyclic quadrilateral. A cyclic quadrilateral is simply a four-sided polygon where all four vertices lie on a single circle. The visual confirms the theorem's rule. If a quadrilateral is inscribed in a circle, its opposite angles are perfectly supplementary. They will always add up to exactly 180 degrees. Circumscription and inscription restrict a shape's degrees of freedom, locking angular measurements to the geometry of the circle. To understand angles intersecting the circle, we first define the space. This diagram shows center O. Points are defined as interior if their distance from the center is strictly less than the length of the radius. If the distance is greater, they are exterior. When two chords intersect within that defined interior space, they form angles that can be measured using Theorem 6.2.2. Notice the two chords crossing inside the circle. The measure of the angle they form is exactly 1/2 the sum of the arcs intercepted by the angle and its vertical opposite. We can test this rule with example 1 from our source material. If the two intercepted arcs measure 84 degrees and 62 degrees, we add them to get 146. Having that total gives us an internal angle of 73 degrees. Intersections that occur entirely within the interior space act as an average of the two distinct boundary arcs they define. If we move the vertex from the interior space directly onto the edge of the circle, the math shifts to reflect this new boundary condition. We start with Theorem 6.2.3. As shown here, any radius drawn to a point of tangency is perpendicular to that tangent line, anchoring a reliable 90-degree intersection. Building on that perpendicular anchor is Corollary 6.2.4. Calculating the angle formed when a tangent and a chord meet precisely at the point of tangency. Because the vertex sits on the perimeter, the angle is exactly 1/2 the intercepted arc. This rule applies universally, whether the chord acts as a diameter straight through the center or sits entirely outside the angle or inside it. By placing the vertex directly on the boundary, the two intercepted arcs we saw previously collapse into a single arc measurement, which is then halved. Returning to the fountain, we can trace imaginary lines along the paths to find intersection points falling in the exterior space, completely outside the basins. Theorem 6.2.5 through 6.2.7 outline a unified principle for any angle formed by two lines intersecting outside the circle, whether they are secants or tangents. Look at the exterior vertex. When the intersection is outside, the measure of the angle is exactly 1/2 the difference of the two intercepted arcs. Theorem 6.2.5 establishes this for two secants intersecting in the exterior. You subtract the smaller arc from the larger and have the result. Theorem 6.2.6 applies the exact same logic when the angle is formed by a secant and a tangent. The formula remains identical. And theorem 6.2.7 completes the set, confirming the rule holds even when both lines are purely tangent to the circle. Moving the vertex from inside the circle to the outside physically separates the intersection from the curve, changing the arithmetic from addition to subtraction. There is one final configuration to account for, theorem 6.2.8, which addresses two parallel lines intersecting the circle. This diagram shows two parallel secants slicing through the circle. The rule here dictates that the arcs intercepted directly between these parallel lines are perfectly congruent. They mirror each other exactly. This split screen tracks the complete logic. If the vertex is inside, sum the arcs and halve. If the vertex is exactly on the edge, halve the single arc. Completely outside, find the difference between arcs and halve. Every angle and intersection around this shape is governed by its spatial orientation to the boundary. The circle is a predictable system, dictating exactly how physical lines and abstract numbers must behave.